For joining us today, everyone. Um, let's actually see if folks are able to get in. So folks are able to get in. That's perfect. So thanks again, everyone, for joining us today, specifically to look at the export of functional mockup units in Dyad and how exactly that works. This, in some sense, is a spiritual successor and a continuation of this webinar we gave previously, which spoke about compilation of Julia code for model-based engineering workflows. Specifically, the technology that we ended up using within this webinar was this new technology called JuliaC, which is being released with Julia 112, Julia version 112. Now, it turns out that you can use the same technology, that you use to export binaries to export FMUs, and that's exactly what we've done here within the Dyad product. And why do we want to do that, right? So you must have seen previous versions of this webinar. If you haven't, the context is Julia and Dyad, for example, take about 15 to 20 minutes to export an FMU usually, and that it usually happens through this open source Julia package called Package Compiler. And Package Compiler does is it compiles a system image. So it says you can see Package Compiler itself is a way of compiling a system image of your Julia code. So in system image is essentially a compilation of your Julia module. So supposing you've developed a Julia package, which is say what a model is, right? Package compiler offers you a way in order to compile that package down into a binary representation which we call in Julia a system image. Now, it turns out that compiling a system image takes about 15 to 20 minutes in Julia in general. And that's how we used to export FMUs. And so FMUs used to take 15 to 20 minutes to compile. That was the old world. Today, we're going to show you how you can leverage JuliaC in order to compile FMUs. And you will find that with JuliaC, you get essentially you get compile times of a minute to 2 minutes, about which is about a 10x improvement, and the FMU sizes, which used to be hundreds of megabytes before, are now tens of megabytes. So you're seeing essentially an order of magnitude improvement in both the compilation time as well as the FMU sizes. So if you're familiar with the Julia ecosystem and you've already tried these types of things within Julia or Dyad, this is in some sense good news. So just to orient everyone, I mean that's specifically what I'm going to talk about today, the FMU export. But to orient everyone, I just tell you a little bit about our product. So Dyad is a product that has two sub-products in some sense. It's a system simulation tool, firstly, right, which has two sub-products. So we have one sub-product called Dyad Builder, which essentially is a graphics first environment where you can drag and drop blocks, connect them together, and simulate them, and which should be familiar to to users of other popular system simulation tools. And we also have Dyad Studio, which is meant for software engineers. And Dyad Studio is the environment where you can take models that you've built up graphically and then export them to various binary format representations. You can use them to tune controllers and then say deploy the control logic as a binary onto your preferred hardware target of choice, and many other things in between, right? And to some extent, throughout, you'll find in Dyad that most of our features tend to get developed and built in Dyad Studio first, and then ported over to Dyad Builder, essentially given a productized sort of feel to it. So that's how things typically work here. Um, so what I'm going to show you today is a way to leverage JuliaC, and for FMU generation through Dyad Studio. The FMU generation is not yet available through Dyad Builder. I mean, that's work in progress, but you'll be able to do this type of FMU export through Dyad Studio. So anyway, just so you're aware, there are two sort of sub products here. Um, and again, just a bit more orientation, what is FMI and so on. But After that, we'll quickly recall some basics. What is FMI? How do you simulate an FMU in Dyad? If you just wanted, somebody has given you an FMU, a colleague, a supplier, etc., has given you an FMU. How do you simulate it in Dyad and sort of look at the results? How do you import? And then secondly, we'll look at how do you import an FMU into Dyad. So uh, you you can currently do that in Julia, but not quite in Dyad. We'll get to the details of that in a second. But really, what you're looking at in point three is the ability to expose input and output ports and connect things around with an FMU. And that's what I'll sort of touch on. And finally, we'll look at the FMU export. And we'll try to spend most of our time in point four, but if there are questions on the other pieces, just feel free to interrupt me or use the Q&A tab here, the helpful Q&A tab. All right. So what is the functional mockup interface? It's a standard used to exchange dynamic models. It's extremely popular, adopted by hundreds of tools. Your favorite system simulation tool is probably it's probably supports FMI, both import and export. Um, and the way FMI works is it provides a standard of C interfaces um, and then the tool essentially would generate a bunch of C code with those appropriate interfaces, zip it up with an appropriate folder structure, and other tools will just be able to understand that. So it's a pretty neat and very useful format. Um, let's see if I can, whoops, let's see if I can go to the website and show you all the tools that are using FMI so far. So you'll see the who's who. So there are different versions of FMI, as you can see, 1.0, 2.0, 3.0. And there are, and I would say a total of 259 tools. So I should probably update my slide. 259 tools supporting FMI in some form or the other. And of course, like if you select specific versions of FMI, you'll see different tools have different levels of support. FMI 2.0 is the most widely supported as of right now, which is why this webinar is going to mostly focus on FMI 2.0, but our APIs and so on. But we support FMI 3.0 as well, and our APIs are pretty much the same for 2.0 and 3.0. So, okay, with that, let's get into what I wanted to show you today. Let me just check if there are any questions. I don't see any, so let's get straight into it. I might need to reshare my screen. Let me try. All right, you should be able to see my Visual Studio Code editor at this point. So let me just double check that that is indeed the case. Yes, it is. Okay. So the first part we're going to look at is how to simulate an FMU. So uh, a supplier has given you an FMU, or a colleague has given you an FMU, or something like that, and you might just want to simulate it. And the way you do that right now within Dyad is go down to Julia, which is using this fmi.jl package. Now, to, to tell you a little bit of the distinction in some sense with Dyad and Julia, Dyad generates Julia code, and essentially, ultimately, it's Julia code that's running at the end of the day. And if whenever you're in this environment here, which is Dyad Studio, essentially a VS Code environment with an extension, you will be able to run Julia, right? And you will be able to run Julia within your Dyad models. You'll be able to run Dyad models within Julia. So all of these combinations are supported. So essentially, Dyad, as you might expect, has first-class integration with Julia. And to some extent, the general rule of thumb is if you're not able to find that Dyad supports something, check whether it's supported in Julia, right? And so in terms of FMI import and simulation, which it's right down at the Julia level. So let me perhaps show you what that looks like. So you'll you'll be able to see here that within Julia here, this is just plain Julia code. So this is a Julia script here. I'm able to load an FMU just using this load FMU command that's just supplied by fmi.jl. And then I can simulate this FMU by just calling fmi.simulate, and it's going to run it in, whoops, must have forgotten to reload that FMU, but you should be able to simulate the FMU by just calling fmi.simulate. Um, and um, and and if you want to specify certain outputs, you can use this field called record values, and you can supply it a bunch of strings. But you're going to have to convert those strings into these things called value references, and you can do that with a simple Julia array comprehension here. So for every variable in this string, you call string to value reference FMU comma this element, and you'll be able to get a list of record values. And these record values are a way to talk to the variables in the FMU. And now you can see what this does is it returns a result object after calling essentially um, uh, some stuff within the FMU. So essentially it's called FMU instantiate and so on. And this is this debug info coming from the FMU, which is enabled by default in Julia. You can turn that off. That's easy to turn off. And then finally, you can call plot on the result, and then you'll see a bunch of signals pop up on the screen here. So, and if you'd like to know a little bit more about the model that's being simulated, it's in our documentation page, which I will link to at the very end. The second piece I wanted to show you was how you could import the FMU as a component model. So what this is doing is essentially loading the FMU and then simulating it. So just calling the APIs within the FMU and then simulating it, much like FMPy. That's just another popular Python-based tool that people use for this. So if you wanted to, say, import this as a component model, modeling toolkit, again, you're going to have to use a Julia script, but modeling toolkit has a function called FMI component, and FMI component will give the FMU some structure. It's not going to give you a whole lot of structure. I mean, all of the variables and the parameters are flattened in this version of the FMU. You will see what I mean in a second. So you can see that uh, motor underscore inertia underscore W. So right, this is really motor.inertia.w. So in a future version of modeling toolkit, it'll support the hierarchy, but right now it flattens everything out. And you can just call compile on that, and you can run this like you would run any other modeling toolkit model. So if you're familiar with doing that, but really what modeling toolkit is doing is mtk compile calls all of the DAE compiler passes on it. So structural simplification, alias elimination, and things like that. All of that, all of that is encapsulated by mtk compile, and then finally to causalize the system, you call ODE problem, and then you can call solve on this. You don't, because it's a co-simulation FMU, you don't really need to specify a solver, but I happen to do that over here. So finally, you can see it'll structural simplify it, and then of course it'll then you can then causalize it with ODE problem. So it takes a second to do the causalization. And then finally, perhaps the most interesting part of this presentation is the FMI export, which I will show you. And you can see there's a handy new tool called use JuliaC equals true that I've enabled. So, and the other thing you might notice here is that I have 1.12 RC3 installed. And that's because JuliaC is supported just by Julia 1.12. So really these FMU capabilities that you're looking at are coming from Julia 1.12. So let's get into that. So actually, this FMU that I've been calling so far has been compiled with JuliaC as well. So one thing we can do is just quickly take a look at it. You can see this FMU is like 59 megabytes, which is much smaller than the typical FMU you're going to see come out of from our system on Julia 111. A comparable version of this FMU would probably be 100 to 200 megabytes, somewhere in that range. But within Julia 112, using JuliaC, you get a 58 megabyte FMU. So to quickly show you how that is being done, again, we're doing the FMU export in Julia itself. There are ways to do this in Dyad, which I will comment on a little bit later, which is where all of this work will be upstreamed. But right now, you can call this via Julia. So after calling mtk compile on your model, you can call a package called FMU generation. FMU generation is publicly available. People can you can download and install it today. Um, you the FMU generation is our standard FMU export library. Um, but now FMU generation enabled with JuliaC can be leveraged by just calling this Julia FMU command. It constructs this FMU object, and it has all sorts of arguments here in terms of which version of FMI you need, whether it's a co-simulation or model exchange, what type of solver you want to ship with the FMU, and so on. And and um, and to some extent, you can see this is an internal API, um, but the way you can leverage it today is by calling these specific commands. So what actually FMU generation does is it creates a template, which is the Julia package, which is then compiled um, into, again, this type of system image type objects. Like, so essentially it's compiling it to a shared object library on this Linux machine, and you can see that generate code will set up all the scaffolding. So all of the model code and everything that's generated by modeling toolkit gets copied over to that template. Um, and then finally, when you say use JuliaC equals true, what it'll do is it'll precompile the particular module, and of course it needs to precompile the model because the model is new. Um, but of course it's precompiled all the other packages that are dependencies of the model in advance, right? So all it does is it needs to precompile the model, and finally you can see that essentially within a minute or so before I'm able to finish speaking that it's able to that it has compiled the FMU. So this sort of is the main result. But what I thought would be interesting is to take a dyad model and do a little bit of benchmarking on it. So I have a simple advection model, and this simple advection model has a structural parameter over here. This is a port of a Modelica library called the Scalable Test Suite. So this is this can be found online and for free. And what I thought would be interesting um, is to sort of increase the value of the structural parameter. And what this does is it just does a simple advection heat transfer across a rod. And this n is essentially controls the number of discretizations. So can I increase n and see how much my FMU export time goes? And so, of course, I have more equations there, right? So a common question we get asked is, well, can you maintain this fast compile time across, even if you have a ton more equations? And I guess we'll find out. So let's start maybe with n equals 2 uh, and compile this, and then let's time see how long this takes. So you can see it's already started pre-compiling the template, which is this FMI binary thing. And now JuliaC is starting to compile, start doing its own thing. And then it gives you some information, and then it starts information of what is included in the FMU. So you see 2.7 megabytes of artifacts are shipped with the FMU, and then there's a whole bunch of Julia standard libraries and artifacts. Now, there are ways to strip some of this out, and especially blahs and so on, and maybe sweet sparse and things like that. And you'll see the FMU sizes get even smaller. So, but right now, having done all of that, what is the FMU size you see? You see 58 megabytes. And so that's n equals 2. So let's look at n equals 4. Hmm. Just a moment while my terminal reconnects here to this remote server. Okay, so n equals 4, structural simplified, and let's see how long that takes. So actually the previous one took, how long did the previous one take? So you can see it's also running FMU checker on the FMU. Huh, for some reason I lost the previous time, but I believe it's around a minute to a minute and a half. See if I can find it. Oops, looks like the new one is done too. But let me. Anyway, the new one took 34 seconds. In fact, it's a bit faster than I expected too. So we're looking at half a minute for that. Let's look at. So one thing you can notice that I'm not timing structural simplify here. So if you include that, that skews the timings as well. But um, this, as you increase this structural parameter, this MTK compile time takes longer, and that's one thing I wanted to point out. But the actual FMU compilation should be less than a minute. So while we're waiting for these compilation results, are there any questions? I think I see one question. Could you please share the Julia scripts used for this demo? Yeah, I can point you to some examples on how you can. Are there any resources available online? So I have a question about how do I simulate FMUs in Julia? I'll point you to some documentation, and perhaps we can have this documentation be sent out to all of the participants as well. So no, thanks for asking asking this question. We will send you some documentation on how to run the FMU. Um, and while it's compiling, I can show you that it's essentially load FMU and FMI.simulate, and with this record values option here. But we'll send this over to you and all the participants. Okay, so how long did this take? So this again took 35 seconds. So you can see that. So let's actually maybe increase this to 200 and see what happens. But you can see that most of the time actually is being spent in this mtk compile command. And you can see that for the most part, you're looking at a base speed of about 30 something seconds in order to compile your FMU. Okay, let's see if um, that's done. So the structural simplification is done there. And let's look at, well, not yet. But once the structural simplification is done, the FMU should start compiling, and we'll look at the time. So this 30 seconds is in contrast to 15 to 20 minutes with Julia 111. So this type of workflow has gotten a lot more tractable. All right. So let's check with n equals 200. Okay. So there's also a question of whether this pre-compilation step of the template itself takes a bit more time, which we will also check here, because 200 is now a 200, it turns out, is actually 400 equations, I think. Ah, no, wait, it looks like it's actually 200 equation. Right now it's starting to zip up, and we get a minute and a half. So it does sort of moderately increase, given the size of the FMU. In fact, maybe one last data point we can grab is 500. Uh, and and then we can see, actually, while we grab 500, we can see how large the FMU is. So again, 59 megabytes looks like the size is not increasing, but perhaps the compilation time increases with the number of equations. But still, we're not looking at the 20-minute mark. Um, so while this is structural simplifying, let's see if there are any questions. Other examples to set in on how to set a vector of input values. I assume so. There's a question on how to set input values while simulating the FMU. Yes, there's documentation on. Actually, let me try and see if I can share the documentation right now. Let's share my entire desktop. And let's see if I can find this documentation for you. Let's see. So if you went to fmi.jl, you can go to, where's the documentation? So fmi.jl is completely open source. So you can look at, for example, inputs here, right? So inputs specifically, say you had an external exogenous forcing function here, you can supply an input forcing function via this argument called input function, and it should just take, you can take it in. Um, and however, sort of, if you think about it, what has actually happened here is that there is a variable already, like essentially an input port here called X force in this FMU. And what it is trying to do is it's saying, it's telling the FMU for this particular input port, set it to this particular value. So you can see this sort of very scripting like approach. It's, really creating you're not really creating blocks and running it. But this is the quick and dirty way of doing it. But if you'd like to really, if you'd like to create an input source block, right, and then connect it to the input, you'll have to do this modeling toolkit approach that I showed you here, which is creating an FMI component, and then you will be exposed to the input ports and output ports, and then you'll have to connect it up. Um, Ideally, of course, you would be able to do something in Dyad. It's something like this in Dyad, right, and where you can import the FMU, get import input ports and output ports within the FMU, and then you would then create a test component that wraps it, that adds inputs to the FMU and connects it up. But again, that's work in progress on the Dyad side. But in Julia, you can do it the quick and dirty way, or you could do it the component based way, this way. Okay, let me check. Should be. I think I've answered this question. So again, looks like it's still structural simplifying. But yeah, I'm sort of, you're looking at a minute and a half, maybe a minute to 2 minutes is sort of the range you would look at for a fairly reasonably sized model. Again, in comparison to the 20 minutes that you were seeing earlier um, with the previous approach. Okay, while this is going on, maybe I will conclude. So this is the content I roughly had for you today. Uh, I what I wanted to leave you with is our documentation, just our Dyad documentation. If you're interested in evaluating Dyad or using it and so on, I would recommend downloading our Visual Studio Code extension if it's approved by the IT department within your company. Um, and if it's not approved, reach out to us and we can help with that. But if you want to look at the Dyad documentation, go to help.juliahub.com. So let's do that a little slower. So help.juliahub.com, click on Dyad, and then there's Dyad language documentation, and you will see how you can get started. You can create a component library. You can give it a name and then start creating models. You can do FMU export from Dyad with the old non-trim JuliaC way. And the way to do that is, let's try and find it, is essentially by writing, by extending a standard analysis called FMU analysis. So if you put this in your Dyad code, it should work, and you can specify a model instantiation, and this will export an FMU of the signed component with these parameters. So this is currently supported in Dyad without trimming. But we'll upstream the trimming work to this, and you should be able to just directly access it within Dyad. Okay. Um, in the meantime, let's see if there are any other questions. Oops, sorry. FMI export, does FMI export support the creation of FMIs for co-simulation? Yes, it absolutely does. You can, so you can, within this FMU analysis, within Dyad, you can say FMI type, CS or ME, for example. So here, you can see even within my script, right? You will, whoopsie. So you can see here that I have an array that supports both FMI co-simulation and model exchange, but it could just be one or the other, and so on. And you can additionally you can specify the solver that you want to package. And here I'm just packaging the Julia solver called SITFI. So yeah, yes, you absolutely can do that. Okay, maybe this I created a really large model by mistake here. But yeah, I mean, like informally, so prior to this webinar, when I tested this out, you'll probably see, a minute to a 2 minute compile time. Okay, I think that's it from me. Any other questions for any other questions today? Otherwise, if if you get a chance, please try out Dyad, check out our tutorials, check out how to install the system. You should have all of the instructions in our documentation page, which is at help.juliahub.com/dyad/dev. You and if you're interested in Dyad and just sort of seeing what Dyad can do in terms of upgrading your system simulation capabilities, um, let us know. Please contact us. In general, we bring the entire Julia world to the system simulation world. Like if I were to sum up a value proposition in one sentence. So if there are things you're trying to do that are declarative on the modeling side, but also imperative, in terms of the analysis side or anything like that. I think we bring the best of both worlds. So let us know if there's any interest, and I don't see any other questions, and we'll check whether this thing is done. Not yet. So I think with that, I will conclude it and say thanks everyone for your time today.